Hi, welcome to our 2.3 video of solving systems of equations. What it means to solve a system is that if you're given two equations, what you're trying to find is the ordered pair that would make both equations true statements if you were to plug in that x and y as its coordinate. Sometimes there's lots of answers, sometimes there's no answer. So we're going to talk about different methods of solving today. Really there's 5 methods if you include the matrix method, but we won't be talking about that one today. Okay, the first one is graphing. What we want to do is graph each equation and then see where the two lines intersect. The first equation is in standard form. I'm noticing the x-intercept would be 4.5 and the y-intercept would be -3. And I prefer to, when I'm plotting with the graphing method, to make sure that I'm plotting integers just so that my graph is a little bit more accurate. So I'm just going to plot the y-intercept of -3. And then I'm going to use the slope to find an additional point on my graph. Okay, how to find slope in standard form. Okay, here's your standard form if we were to subtract ax from each side and then divide both sides by b. We see that the slope would be -a over b. So in the original equation, if you just take the opposite and it's the ratio of a over b, then that can tell you the slope. So with our equation, the slope would be the opposite of -2, so that would be a +2, over b, which is 3. So our slope is 2/3. How I can use it on my graph is to use rise over run of slope to find an additional ordered pair. So from my ordered pair given, I'm going to rise by 2 and then run by 3. Maybe I'll do it one more time. Rise by 2, run by 3. Okay. So try and be as accurate as you can when you're graphing with the purpose of solving a system. So this is our equation 1. Now graphing equation 2 will probably be a little bit easier. It's still in standard form, but I notice that both the x and the y-intercepts are 2. Okay, there's equation 2. Like I said, when you're solving a system, you're looking for the ordered pair that makes both equations true. In this case, it looks like our graph is intersecting at 1, 2, 3, at 3, -1. And it's important when you're graphing that you need to verify your solution because your lines could have been just a little bit off. Maybe it looks like it's 3, -1, but maybe not exactly. So the way that you verify is to actually plug in that ordered pair and make sure that it really is in fact a solution to both equations. So we're checking with the first equation, -2 times 3 plus 3 times -1. Does that equal -9? Okay, this is -6. -3, that works. Okay, so we know it's a solution for the first equation. Let's check the second equation. That'd be 3 plus -1, does that equal 2? Yep, that does. So 3, -1 is our solution. All right, the next method that you can use to solve a system is with a table. Depending on the equation, this may be easy, maybe not. But what you're looking for is, once again, with the same x value, when will they have equivalent y values? So you're looking for that same output for your equations. What's helpful is the way that I've designed this table is that x is the input and then y is the output. So with the second equation, I'm going to solve for y by subtracting 10, or subtract x. And I'm going to distinguish them as y sub 1 and y sub 2 for my equations. Okay. I just start at 0 when I'm testing, and it gives me kind of a grounding, a ground zero point that I can look at and see where, if I need to go up or down from here. So if I put 0 in, 0 minus 2 is -2, 10 minus 0 is 10. right now my y values are 12 units apart. I need them to be equivalent. So let me try 1. Okay, 1 minus 2 is negative 1. 10 minus 1 is 9. My y values are now only 10 units apart. So I can picture that on a graph as like they're getting closer to each other because the difference between the y values are getting smaller. So I know I'm going in the right direction. If this were a bigger difference than 12, what I would want to do is check negative 1 and negative 2. Okay. I know I've got a ways to go, so maybe I'm going to jump to like 4. And if I need to, I can cut back again. So if x is 4, 4 minus 2 is 2. 10 minus 4 is 6. I'm now only 4 units apart. So once again, I'm in the right direction. Maybe I'll try 6. So 6 minus 2 is 4, and 10 minus 6 is 4. We got it. So we were looking for when the y values were equivalent. So our solution is 6, 4. When we have an input of 6, the two equations are producing the same output of 4. So 6, 4 would be our solution. Okay, algebraically, what we can do is talk about substitution or elimination. So these are two different methods that you can use to determine your solution. With substitution, your first step is to isolate a variable. So what that means is to write one of the equations as y equals or as x equals. This one is already written as y equals, so we can skip that step. From here, we want to use substitution. Okay, x plus 9 is an equivalent way of writing 9. So by substitution, I can substitute x plus 9 in the spot of y. Okay, so it would look like 4x plus 7. But instead of y, I'm going to write x plus 9 equals 19. So from here, I'm going to solve for x. Distribute 7. So 4x plus 7x plus 63 equals 19. 4x plus 7x is 11x. And then I'm going to subtract 63 and get negative 44. And then divide both sides by 11. X equals negative 4. Okay. We found half of our solution. It's negative 4 comma something. Now that we have the x coordinate, what we can do is go back to either equation and plug it in for y, or plug it in for x. So y equals x plus 9. I'm just going to pick the first equation. And I'm going to replace x with negative 4. Negative 4 plus 9, y equals 5. So the solution to this equation, system of equations, is negative 4 comma 5. I wanted to show this as well. It's technically substitution, but when you have both equations solved for y, what you can essentially do is substitute the y value, and by doing so, you just set the equations equal to each other. So 2x minus 1 is equivalent to y, so we can write this as 2x minus 1 equals negative 1/2 x plus 4. So when you set both equations equal to each other, it's because they're both equal to the same variable. What I'm going to do is get rid of the fraction as my next step. So I'm going to multiply everything by 2. So we get 4x minus 2 equals negative x plus 8. Add x to both sides. Add 2 to both sides, and then divide by 5. X equals 2. And now that I know my x coordinate, I can go into either equation. Maybe this time I'll use the second equation. And replace x with 2. Negative 1 plus 4, y is 3. So our solution to this system is 2, 3. All right, so that was substitution. The other method that you can use to solve algebraically is to use elimination. The idea with elimination is traditionally you want to get it in standard form, but it doesn't have to be. Really, all that needs to happen are the x variables are in the same spot, the y variables are in the same spot, and the equals is in the same spot. So if you had them both like this could also be used, or you could also solve this with elimination. Okay, with elimination, you want to add the equations together so that you've eliminated a variable. Okay, the whole point is to take this from 2 variables down to 1 variable. However, if I were to just add these equations together, I'm not going to eliminate anything, am I? Like 2x plus 6x is 8x, y plus negative 5y is negative 4y. So I would still have an x and a y variable in my system. So I need to multiply one equation by a constant so that when I add them, the coefficients will cancel out. I am going to multiply the first equation by 5. And by doing so, I'm kind of looking ahead here, this is going to become 5y, and then when I add it with negative 5y, I'm going to eliminate the y's. So multiplying everything by 5, I'm going to get 10x plus 5y equals 100. And then we'll have 6x minus 5y equals 12. Okay, it's important that when you add that the two terms have opposite signs. I see sometimes students have like plus 5y and plus 5y and they just think about like subtracting the terms. Well, that would work if you remember to do it to every single term, which sometimes doesn't happen. So I'm going to add 16x, the y's are eliminated, 112. 112 divided by 16 is 7, so x equals 7. Now that I know x, substitute it back in, maybe the first equation, 2x plus y equals 20. I can do 2 times 7 plus y equals 20, subtract 14 from each side, y equals 6. So my solution here is 7, 6. Sometimes you only have to rewrite one equation, sometimes you have to rewrite both. Notice with this one, all 4 the values of a and b are positive, so I'm going to have to multiply one equation by a negative. And also, there's no way to just multiply 2 unless I want to get into fractions to get it to equal 3. So you can choose to eliminate the x's or eliminate the y's. I'm going to go for x's. So I'm going to look at 2 and 3 and say what's the smallest number that both 2 and 3 go into. That would be 6. So the idea is I want this to be written as 6x and then like a negative 6x, so that when I add them together I get 0. With the first equation, if it was 2x and I want it to be 6x, I'm going to multiply that by 3. Then we have 3x and I want it to be written as negative 6x. That means I need to multiply by negative 2. So continuing on, we have 2x times 3 was a 6x, plus 21y equals 12. And then with the second equation, be careful when you're multiplying by a negative about the sign changes. So it's negative 6x minus 10y equals negative 5 times negative 2 is positive 10. When we eliminate here, we're going to get 11y is equal to 22. Y is equal to 2. Substitute y back in. So with the first equation, 2x plus 7y equals 4. This should be 2x plus 7 times 2 equals 4. I can subtract 14 from each side. 2x is equal to negative 10. X is equal to negative 5. So my solution would be negative 5, 2. Okay. All of our examples today had just a single ordered pair as its solution. What we're going to look at tomorrow in class is the special cases. So what would it look like to have infinite solutions, and what would it look like to have no solutions, and then how can we identify those with their terms. All right, that's it. Thanks.